In this tutorial we're going to talk about magnetic flux. And flux in general has the same concept no matter if it is electric or magnetic, in this case flux. So we have a surface and we're going to be accounting the amount of lines of field, in this case is magnetic field, that are passing through a certain area, right? And once again, this is a scalar, so as well as we did with the electric flux, the magnetic flux is going to be equal to the field in a dot product with the area. So remember that this is, for instance, B times A times the cosine of the angle between B and A. And in any sense, for instance, if B and A are perpendicular, there is no flux, but if they are parallel, the flux is maximum, and it also depends on the angle, for instance, between the magnetic field vector and the normal vector of the area. The units of the magnetic field are, for instance, Tesla times meter squared, which are called Weber. Remember as well that if we have a vector of magnetic field which has component x in I plus component y in j plus component z in k, and a vector area, a normal vector of area, which has component x times component y times component z, right? Remember that in the dot product we only have to multiply, for instance, component x times component x plus component y times component y plus component z times component z, and this will give me a number which is a scalar. And in the same sense that we did, for instance, with magnetic field, there is Gauss's law. And Gauss's law, for instance, will state that V dot dA in a closed integral of surface, right? Do you remember that in, for instance, Gauss's law in electricity equaled the charge enclosed over epsilon 0, but in this case, everything is going to be equal to 0. This is Gauss's law. So Gauss's law for electricity was E dot dA, the sum of all the fluxes. It was equal to the charge enclosed over epsilon 0. But instead of having, for instance, the electric field, we do the electric field. This is equal to 0. Why? Well, imagine we have a magnet, right? And we have a north pole and a south pole. And the lines of magnetic field will start to move, for instance, from north pole to south pole, right? In any given magnet. So, if we enclose, for instance, the lines of magnetic field in the surface of this magnet, well, all the lines that go out will enter once again the magnet. And what happens, for instance, if we grab the magnet, right, and we cut it in two? You might say, well, then we have one north pole and one south pole. But what happens later in life, right, is that we will have two magnets, and both magnets will have its south pole and its north pole. So in that sense, once again, all the lines will be, for instance, going from the outwards in the north pole towards the inwards in the south pole. And once again, the lines in magnetic field in the magnet, well, what enters or what goes out from the magnet will enter again. So this will mean, for instance, that there are no actual sum of magnetic lines of magnetic field in this enclosed area. And that its only meaning is that there are no magnetic monopoles. There are no magnetic monopoles. So in that sense, the Gauss's law for magnetism will state this truth. There are no magnetic monopoles. All the flux that goes out from one pole enters into another pole.